When a process variable has only random variation, each output is independent of the previous one. This is what happens in a lottery. In some processes, this independence does not happen. If we control our daily weight, for instance, our weight today is correlated to the weight of the previous days, it has autocorrelation. One common case of autocorrelation is shown by our body weight. Our weight today is correlated with yesterday's weight, 53%. The day before, 39%. Body weight has inertia, you don't expect sudden changes. A similar effect happens when you control a heavy aircraft or a ship. Its massive weight prevents you from making a sharp turning, or make a sudden stop. This opposing force to change is what is called inertia. The inertia definition applies to moving objects, and it is proportional to the object mass. Inertia also applies to fluids. A tank accumulating a fluid will also have this inertia effect. We will now experience how to control a process with inertia, with a simulator of the tilt control in an airplane. Download this Excel file inertia simulator.xlsm from OneDrive. Close other Excels, and allow macros to run it. Press Start to start simulating. Move the cursor up and down to adjust the tilt, do not click. You should try to keep tilt as close to 0 as possible. The graphs below will show you the adjustments you made and the actual tilt evolution along 50 runs. The average and standard deviation on top will tell you the extent of your success. You want both to be minimal. We have produced the following results after 50 runs. We experienced the difficulty of reacting to this random behavior. We notice there is a delay in the response which drives us to overadjust. The histogram of the actual tilt evolution is. It is a normal distribution with an average of 1.47 and a standard deviation of 4.01. We analyze the evolution of tilt along time with an SPC chart. It shows some out-of-control situations. Let us now measure autocorrelation of this data with Excel data analysis. Each value is correlated with the previous one with a correlation index of 44%, this means there is a strong autocorrelation. This confirms the inertia effect due to the mass of the airplane. Let us compare this with a purely random process with a normal distribution. In this case, there is no evidence of autocorrelation, each outcome is independent of the previous ones. When you try to control this process, the first thing you notice is that there is a delay between your adjustments and the tilt response. This is the result of inertia, the response is slow. Let us now analyze another example. By accumulating a fluid in a tank, we achieve a balancing effect, which is useful to reduce the standard deviation of a critical metric. We want to control the pH of drain water in a factory. Pure water has a pH of 7. Some local regulations require that water pH should be between 5.5 and 9.5 before it can be drained into a river. In the following example, accumulation in a tank has been used to reduce the pH standard deviation, to meet the required regulations. The sewage water from the factory has an average pH of 5.68 with a standard deviation of 2.09. According to the previous regulations, specs, the resulting CPK is 0.086, which is clearly unacceptable. We will often contravene the regulations. This is an histogram of the pH of the factory sewage. After the sewage was accumulated in a pond, we compare the pH of the input into the pond with the pH of the output drained onto the river. We can see that variation has been significantly reduced. The pH histogram of the output is now, resulting in an average pH of 5.99 and a standard deviation of 0.42, which gives a CPK of 1.17, a significant improvement from 0.08. We can see a significant autocorrelation in the output, produced by the pond accumulation. This had a positive effect in reducing the standard deviation of the pH, to meet the regulations. If we want to control a process variable with an individual's control chart, we have to meet two prerequisites. It should follow a normal distribution. Each output should be independent of the previous ones, no autocorrelation. In the following example, we have been measuring a critical process variable, dye water resistivity. We have been measuring a critical process variable, dye water resistivity, with the following results shown in an SPC individuals chart. We notice continuous out-of-control situations which are mostly false alarms. Download this Excel file resistivity.xlsx from OneDrive. There is significant autocorrelation. If we want to use SPC to control this process, which has significant autocorrelation, we can apply exponential smoothing EWMA to the data. To do this, we will calculate the transformed EWMA of resistivity, where lambda is a number between 0 and 1. We will use Excel Solver to calculate lambda to minimize the residuals in column C. Now we ask Solver to minimize the total error in E2 by calculating lambda in D2 with the restrictions that it should be between 0 and 1. We obtain the result of lambda equals 0.284. Now let's see the original resistivity and transformed EWMA in a graph. We are now going to use the resulting residuals in an SPC chart to control the process, instead of the original resistivity data. We have now removed the false alarms from the SPC chart and we keep only the real out-of-control symptoms. We see no significant autocorrelation in the residuals. So, this enables us to use an individual's SPC chart with the residuals, to detect out-of-control situations of the original data, without the false alarms. These are some conclusions. Process inertia shows with autocorrelation, metric values are dependent of previous ones. Inertia causes a delay between action and response, which may produce overreaction when you try to control the process. Mechanical inertia is proportional to the mass of the object, airplane, ship. Fluid inertia is proportional to the volume of its storage in a tank or pond. A flywheel is used in a car engine to smooth rotation speed, by increasing mechanical inertia. Fluid accumulation in a tank is used to reduce variation. Body weight has autocorrelation. Autocorrelation could have a positive effect, it reduces standard deviation. To control an autocorrelated variable, it may be transformed by exponential smoothing, then we control the residuals instead of the original variable. All this can be done with Excel data analysis and Solver. You can see this article in Polyhedrica blogspot.